Now, before you do any question on calculation, it is very important to read the text and also study the diagram if there is one, for you to understand what is going on. Now, reading the text and then studying the diagram allows you to obtain information that you need to solve the problem, information that you need to select the appropriate formula or the appropriate principle to use in solving the problem. So let us study this problem and then solve it. The demolition ball of mass 1250 kilograms. Now, and when you read problem, you use the unit to identify the information that is given. This kilogram means that it is a mass. The mass of the ball is 1200. So they are talking about this ball. It's a heavy object. It's lifted by the crane to a point R at a height of 5.8 meters. This 5.8 meters is showing you that this is what a height or a distance above its lowest point in 60 seconds. This 60 seconds is what time taking. Time taking. So it means that initially this ball was here, it was hanging at rest here, and then this crane provided the power to lift it up from here up to its position here. And what we need to know is that before it was lifted, it was at rest. Then after it has been lifted to position R, it also stops, so it comes to rest. And then the speed at the lowest point is 0, and then the speed at the highest point is also 0. Then we go to the questions. Define the term power in words, and the definition of power is known, and then that is the rate at which work is done. So that is as simple as that. Then let's go and then look at the second question, which is 1.2, and then it says calculate the average power dissipated by the crane in lifting the demolition ball to point R. So what is the average power dissipated by this crane? Now what we need to know is that this crane exerted an applied force on the ball to lift it from its lowest point to point R. And applied force F is a non-conservative force. So let's see the information that we have. We have information about the mass of the ball. We have information about the time taken for the ball to be lifted from its lowest position to the highest position. Then initially it was at rest. That is what you have to understand. And then after it was lifted here, it also comes to rest, and then it is hanging like this. Then we have the height, which is 5.8, and then this movement or this motion occurred in 60 seconds. So if we have to calculate the average power, the symbol for power is P. Then we have to go to the formula sheet, and then we see which formula will be appropriate. Now, there are two ways we can calculate average power, and the first one is power is equal to work done divided by time taken. The second one is power average is the forward force times the average velocity. Now it seems that this one will be more appropriate because we have information about the time taken. So it is good we choose this one, and then we write it, and then we try to work out other unknown variables. So we say that power P is equal to work done divided by what? The time taken. But let us remember, work done by what? Work done by a non-conservative force. Now we are talking about the work done by the crane, because it's the crane that lifted the object from its lowest point to the highest point. So this crane provides exerted a non-conservative force, which is an applied force. So we say that work done by non-conservative force is equal to change in potential energy, that is this one, change in kinetic energy plus change in potential energy. But as we said, that the demolition ball initially was at rest, that is at its lowest point, rest. Then after it was lifted here, it's also stopped, so it came to rest. Then the change in potential energy is zero. Therefore, our formula for work done by the non-conservative force becomes a change in potential energy only. Change in kinetic energy is zero. So we say it's going to change in potential energy divided by the time taken, which is mg times the change in height divided by the time taken. And then when we substitute, the mass of the ball is 1,250 times gravitational acceleration, which is 9.8, and then the height of the ball, the final height is 5.8, initial height is 0. And then when we multiply that and then divide by the time taken in seconds, we get the power to be 1,184.17 watts. Then let's look at the next question, which says that the demolition ball is released, which means after it was lifted and it was at rest. Remember what we said, that you must read the question, study the diagram to understand what is going on. The ball is now released from point R, and then it strikes the wall at the lowest point of its swing. So it strikes the wall, it comes from here and it strikes the wall. Then what happens? The ball then moves 0.25 horizontally into the wall before coming to rest. So it strikes the wall here, then it moves inside 0.25 meters, which is 1/4 of a meter, before coming to rest inside the wall. So what do we get from this information? We see that this ball initially was at rest, it was released, it hit this wall, crashed it, went into it, and then came to rest again. Now, let's see, define the term non-conservative force. And non-conservative force is defined as the force for which the work done in moving an object between 2 points does not depend on the path taken. Now, what we need to remember here is that in mechanics, we have the gravitational force as the only non-conservative force, especially for our work at this level. Let's say that the only non-conservative force is the gravitational force. So the force you are referring to here is the gravitational force, and that is the work, the force that brings it from point R, that is after it was released, it moved under the influence of gravitational force only. Because you see, there's an information here, ignore air friction. That means it was not stopped, or no other force acted on it. So it was released under the influence of the gravitational force, which is a non-conservative force, and then it came to hit the wall, got into it horizontally, and then came to rest. So that is it. Then we look at 1.4. Is a force which the wall exerts on the ball a conservative or a non-conservative force? Now, let us remember that in mechanics at this level, the only conservative force that we have is what? The gravitational force. Now, the wall exerts a normal force on the wall, on the ball. The wall exerts normal force on the ball, and normal force is not conservative. It is non-conservative. The only force that is conservative is what? The gravitational force. Then we go to number 1.5. State the energy conversion that takes place during the downward swing of the demolition. Now, once again, ignore air friction. This is very important because it suggests that this system is isolated, or the net external force acting on in this system is zero. Therefore, the mechanical energy of the system is conserved. In other words, the total mechanical energy at the top here is the same as the total mechanical energy just before it struck the wall. So, what is the energy conversion that takes place? It is from the potential energy. Remember, the mechanical energy is the sum of potential and kinetic energy. So at the highest point, when it is still at rest, all the mechanical energy is potential energy. Then when it starts to lose height, that is as it starts to move downward, its speed increases. So we are losing potential energy, and then we are gaining what? Kinetic energy. So at the lowest point here, where the height is zero, we have a maximum kinetic energy or maximum speed. So we say that the energy conversion that takes place during its downward swing is from potential energy, that is height, to kinetic energy, that is speed, from maximum height to maximum speed. So we have from potential energy to kinetic energy. Now, the 1.4 we said non-conservative force, and then 1.5 is from kinetic energy to potential energy. Then let's look at the last question, which is the calculation. Now, using energy principles, normally this is what they will tell you. Using energy principles, you have to know which energy principles or principle will be applicable. Calculate the magnitude of the average force exerted on the ball while it moves into the wall. Now, this ball moved horizontally into the wall before coming to rest. So what information can we get from this part of the statement of the problem? Now, the information we can get is that it came to rest. It has a final velocity of 0, but it did not hit with a 0 velocity. It hit with a velocity greater than what? 0. If the velocity is 0, it cannot crash into the wall. So that's what we need to know. We need to know the velocity with which it hit. Then we see the displacement, the horizontal displacement. That means there is no vertical motion involved, but it's only what? Horizontal motion. So we have the displacement horizontally, we have the final velocity, and then we need to get the initial velocity, and then we can use the work energy theorem. Since we have a final and initial velocity, there's a change in a velocity. It means there will also be a change in what? Kinetic energy, which means the work energy theorem will be applicable once there's a change in kinetic energy, and there's no change in potential energy. So we can go and then say that the displacement, we have 0.25 meters, and then the final velocity, that is the velocity inside the wall of the ball, inside the wall, is 0. Then initial velocity, we calculate. I will show you how this was calculated, and then what is the force, the average force that stopped it. Now, because we were told here that the system is isolated, it means that the velocity, how do you call it, mechanical energy of the system is conserved. In other words, the total mechanical energy at the top here is equal to the mechanical energy at the bottom just before it struck the wall. So we apply the principle of conservation of mechanical energy to find the velocity with which it struck the wall, and then that becomes our initial velocity before it finally stops with a final velocity of 0. Then we say that um, mechanical energy at the top, that is point R, is equal to mechanical energy at the bottom. Then let's remember that this one formula, we don't have it on the formula sheet, but we use the principle of mechanical conservation of mechanical energy, which states that the total mechanical energy in an isolated system is when there is no non-conservative force, there's no friction, there's no applied force. This ball came down under the influence of gravitational force only. That is where we apply the principle of conservation of mechanical energy. So we go to the formula sheet and then let's see how we can form this formula. Remember, mechanical energy is the sum of potential energy EP, which is mgh, plus kinetic energy, which is ek, half mv square. So we say that the sum of this is going to be mgh plus half mv square is my uh, uh, mechanical energy at the top is equal to EP plus half, that is mgh plus half mv square at the bottom. So let us see how we write it. We expand this formula. Now that is mgh plus half mv square at the top is the same as mgh plus half mv square at the bottom. And then when we substitute, m is the mass, g is the gravitational acceleration times the height, that is at point R, plus at the top it was at rest, it was released. So if I substitute 0 into, which is the velocity, into this expression, everything here becomes 0. So I can just say 0 plus, now at the bottom, my height is 0. My height is 0. So if I substitute 0 here, it makes everything here to disappear. And then that becomes 0 plus half the mass times the velocity square. Then if you use your calculator, you will find that your velocity is going to be, or your speed is going to be at the bottom will be 10,662. There are other numbers, but I just did not write it. And then that gives me my initial velocity, the velocity with which it struck the wall. Then now I'm going to use this one with the final velocity. That is when it came to rest. And then the displacement, or the horizontal displacement, and then find the force that brought it to rest. Let's go back and check what the question is. It says, using energy principle, calculate the magnitude of the average force exerted on the ball while it moves into the wall. This force is the force exerted by the wall as it crashes into the wall, and it is exerted in the opposite direction of the displacement. Remember, this ball went horizontally to the right, but the force experienced is to the left. So let us understand this, that the force is a stopping force. It is in the opposite direction of the displacement, and then we can use it now to write the formula, and that is the work net is equal to change in kinetic energy. Remember once again that we are using this formula because there is a change in kinetic energy. A final velocity is 0 and then the strike velocity is not 0. So that means net work, or a work net was done. And then we say that the expanded form of this formula is now the force that does the work times the displacement. Remember, work done by a force is W, which is work, F times the displacement times the cosine of the angle between the force and then the displacement. So at the work side of the formula, we have F times the displacement times cos theta is equal to, then the change in kinetic energy side is equal to what? The final kinetic energy, which is final mv squared, uh, minus initial mv squared. Then when we evaluate that, when we substitute, we say that the force F is equal to this. We substitute the displacement times cos 180 degrees. 180 degrees. Why 180? Because we said that the force acted in the opposite direction of the displacement. This is stopping force. Is equal to, then final kinetic energy is 0 because the final velocity is 0, minus the initial kinetic energy, that is the strike velocity, the strike kinetic energy, and that is 1/2 times the mass times 10,662. Now, when I did this, I did not use these numbers, but I used the exact figures that the calculator gave me. So when you evaluate, you are going to get the force or the average force to be 284,200 newtons. And that is the solution for this problem.